Welcome back to Pratik Academy. In last video, we have started with our some sample numericals. So continue with that part. So, next example is based upon rotor, mass, and spring system. So in this arrangement, there is one spring which is passed over one rotor which is hinged at this point. So it can only able to rotate. There is no any linear motion of this rotor. It only rotates, and one this spring, and there is a string. This part is only spring, and one string is passed over this rotor, and this string is unstretchable, and mass is attached to one end of this string. And they have asked to find out what is natural frequency of system. So in these types of problems, we will go for energy method. This will be very easy. Now by energy method, this method is total energy of system at any instant is constant. So total energy here, when we deflect, consider we deflect this mass by amount say x, then spring also deflect by amount x, because this string is unstretchable. Okay, when we deflect this system or mass by small amount x in downward direction, this rotor will rotate because this string is passed over this rotor. So due to rotation of rotor, it is getting kinetic energy, rotary kinetic energy. Due to movement of this mass, it gets linear kinetic energy, and due to stretching of this spring, it gets potential energy. So total energy in system at any instant will be kinetic energy of mass, spring strain energy in spring, and rotary kinetic energy of rotor. Okay, now so this will be constant. Now consider when we deflect this mass by amount x, then this spring or this string will move by amount x here. That means this arc is x. Then angle subtended at center will be given by x is equal to arc theta, or arc is equal to x r theta. So this will give relation between linear displacement x and rotary displacement of this rotor. Okay, then x dot, taking derivative as r is constant, it will come x dot will be equal to r theta dot, and x double dot, it is linear acceleration, is equal to r into theta double dot. So this is the relations. Now first calculate kinetic energy of mass. So this is simply 1 half m x dot square. Okay, but x dot is equal to r theta dot, so it will come to 1 half m here, as x dot is equal to r theta dot here. So putting this value here, you get kinetic energy of mass is equal to 1 half m r theta dot square. This is the first problem. So first equation we get is equal to 1 half m r square theta dot square. Okay, then next, strain energy or potential energy of spring, that is equal to 1 by 1 half kx square. Again x is equal to r theta, and equation becomes 1 half k r square theta square. This is the third equation. Then kinetic energy of rotor. So this rotary energy is rotary kinetic energy, so it is equal to 1 half I theta dot square. And putting these values in equation 1, we get 1 half I theta dot square plus 1 half mr theta dot square plus 1 half k r square theta square is equal to constant. Then differentiating this equation and equating to 0, we get this. After differentiation, we get this. Okay, now cancelling common terms, we get here this equation. Then collecting terms containing acceleration, it is theta double dot, we get theta double dot is in here, so this I and m r square, so m r square plus displacement term separately k r square theta. So dividing this term we will get equation in form of theta double dot plus here theta double dot plus kr square upon mr square plus I theta is equal to 0. And comparing with our standard equation is theta dot double dot omega n square theta is equal to 0. We get natural frequency as under root kr square upon I plus mr square. So this is for natural frequency. Okay. We consider here our pulley or rotor is fixed or hinged at one fixed point. Okay, so let's consider this arrangement. Okay. Here again we have one pulley or rotor attached to spring, and one unstretchable string is passed over this pulley and connected to mass here. Then we have to find out its natural frequency. Here again find natural frequency. So again by energy method, total energy of system remains constant. Then let's consider if we deflect this mass, or suppose when spring is deflect by amount x. Okay, when spring will deflect amount x, then this pulley will also deflect by amount x. So that means it performs linear displacement amount by x. Now the string in this side both will goes in downward direction, so mass will deform by total amount, say dx. It is when spring extends by x amount, mass will lower by x amount, but mass of this small mass or rotor will deform by x amount, and this mass is lowered by double amount, that is 2x amount. Okay, that is when spring lowered by x, rotor lowered by distance x, but mass lowered by distance 2x. Let's call it as y. So here total length passed over is m. That means rotor is rotated, subtended arc is equal to 2x, and it is equal to y. So arc subtended at rotor center will be r theta is equal to y is equal to 2x. Okay, so this is important. Here mass is performing both linear motion also and rotary motion also. Here and total energy of spring solar system is kinetic energy of mass, kinetic energy of rotor, and potential energy of spring as it is. Then kinetic energy of mass, as mass moves by amount y here, then it is equal to 1/2 m y dot square. Then 1/2 y is r theta, then y dot will be r theta dot, and y double dot will be r theta double dot. Putting these values we get kinetic energy of mass here 1/2 m r square theta dot square. Okay. Then potential energy of spring, is equal to 1/2 kx square, but as k is, so x is half of y, so it is equal to 1/2 k y by 2 square, and again it will come 1/2 k y square by 4. Putting value of y here in terms of theta, we get equation 1/8 k r square theta square here. So this is the third equation. Then next is the kinetic energy of rotor. Rotor is having both linear kinetic energy and rotational kinetic energy. Linear displacement by x amount, so it is equal to 1/2 capital M x dot square, and angular motion is theta, so 1/2 I theta dot square. So converting this x in theta, first is x dot is half of y dot, then squaring we get this term by putting values, corresponding values. Finally we get 1/8 capital M r square plus 1/2 I bracket complete theta dot square. This is the fourth equation. Then put these values 2, 3 and 4 in equation 1. We get here it here 1/2 m r square theta dot square. This is for rotor, total energy of rotor. This is for spring mass. Sorry, this is for or this is small m. Sorry, this is small m. This is for our mass, and this is for our spring, and this is for our rotor, linear and angular kinetic energy. Then again taking derivative and equating to 0, we get this equation. Then at this stage collect all terms containing theta double dot. So here we have already collected, so equation becomes here 1/2 m r square plus 12 capital M r square by 16 theta double dot plus 1/8 k r square theta is equal to 0. Then converting it into standard form, we have to divide this term to this term. Then the containing equation, if we compare this equation with our standard equation, then natural frequency will be under 1/8 k r square upon 1/2 capital M here plus 6m, sorry, with a small m here. This is mass of weight, and this is the mass of rotor here. Then solving these terms, we get final equation omega n is equal to under root k upon 4m plus 3 capital M. This is for our this arrangement, natural frequency of this arrangement. Here total energy, here remember mass is having both linear motion as well as angular motion here. So let's check another numerical. So this is again simple one. Here again ask neglect mass of pulley and find natural frequency. So in last arrangement or last two problems, here there is a single spring, so we can calculate deformations of this m and this m easily in terms of spring. Here also there is a single spring, so we can easily find out these deformations. Okay, but here in this problem there are two springs separately. That means here deformation is separate and here deformation is separate. So this method, or in this type of problem, it will not be easy to solve by our energy method. So here we use deflection method or equivalent deflection. Suppose when there are two or more springs, use this deflection methods. Okay, now consider del is deflection of mass, then this deflection of mass will be equal to deflection in spring 1 plus deflection in spring 2. Okay, now equation is deflection in spring 1 plus here 1/2, because this spring is unstretchable. When this spring, suppose say, deflects by x1 amount, then half of this x1 amount will be usually in this side. So net deformation of this mass when spring deflects by amount x1 will be x1 by 2. So our mass when spring lowered by del amount, our mass lower by del by 2 amount. So deflection of mass is equal to this deflection plus half of deflection of spring 2. So our equation will be deflection of mass is equal to deflection in spring k1 plus half of deflection in spring 2. Then as this weight is, we have neglected this weight, then consider deflection of spring k1 separately. Here mass is attached to m, so its weight will be, suppose say f. Okay, that is nothing but w. Then deformation is equal to force per, per spring constant, that is F upon K1, is equal to deflection in spring K1. Okay, then if you consider this spring K2, here weight is attached to this pulley and this pulley is supported by two strings. Then this weight will be equally divided into these two springs. Then weight force acting on this spring will be half of weight. Okay, that is F by 2. Therefore force is F by 2 here and spring stiffness is K2. So deflection will be equal to F upon 2 K2 here. And putting these values in our equation, we get deflection of mass is equal to F upon K1 plus 1 by 4 F upon K2 here. Then it becomes F upon Ke, it is equivalent system, is equal to F upon K1 plus 1 by 4 F upon Q2. Cancelling common terms, get 1 by Ke is equal to 1 upon K1 plus 1 upon 4 K2. Then solving for Ke, you get here this system is equal to 4 K1 K2 under root K1 plus 4 K2. So this is the system equation for vibration for this system. Remember that here two springs are there and deformation in this spring is independent on deformation in this spring. At that case we use this equivalent deflection method. Okay. Now one problem remaining from last video we'll take here. Here find equivalent spring for following arrangements. This is again one mostly asked question in exam. Here arrangement is given, there are numbers of springs arranged and we have to calculate equivalent spring. Then we have two relations, that is series arrangement and parallel arrangement. Then start any one jaw section supported to or attached to support and solve one by one loop or parts. Then if you consider first this part, these two springs are connected in series, then their equivalent will be equal to 1 by Ke equal to 1 upon K1 plus 1 upon K2. Putting values in this equation, we will get here 2K by 3. So these two springs replaced by single spring. Then this spring is in parallel with another spring. So for this we will use relation Ke is equal to K plus K1 plus K2. So solving this we will get here 5K by 3. Then these two springs are connected in series, so 5K by 3 is connected to next spring, and again use this series relation, we will get for this system equivalent spring will be 5K by 8. Then these two springs are in series with next spring, so apply parallel relations, then we will get here 13K by 8. Then again this spring and this downward spring are in series. In solving we will get final single spring having stiffness 13K upon 12. This single spring will represent equally to our given system. So this is our equivalent spring system. Here we have solved or started from one section and solving for each section by parts. We have converted total system to single spring mass system. This is the for equivalent spring mass system arrangement. So equivalent spring. So in this video we have see some examples. In next video there are 2-3 numericals are there. We will see that in next video. Thank you for watching.